Welcome to the first video for this part of the course. The topic we want to cover today is Dijkstra's algorithm. This is a classical design that aims to compute the shortest distance from a given vertex to every other vertex in a weighted graph. So let me jump into the setting. We will be presented with the weighted graph G and a special vertex S, which we will call the source vertex. We will assume that every weight in this graph is a non-negative number, meaning 0 or more. We will discuss in lectures why this assumption is important and where the algorithm will fail in the case that we have negative weights. And I will mention a couple of names of other designs that will handle this case. But for now, focus on non-negative weighted graph. We are also given this special vertex, and our task is to compute the distances from S, the source, to every other vertex T in the graph. Now, what is the distance? Remember, is the length or the weight of the shortest path from S to T. Now, shortest means the total weight of that path is minimal. It doesn't mean that the number of edges involving or to make that path have to be minimal. You can have a very long path in terms of the number of edges, but the weight, which is the sum of all the weights of these edges, is what matters here. And what Dijkstra proposed was to do this in a greedy approach. He said, well, I am sitting at vertex S. I'm going to get to every other vertex in an optimal way. I'm going to start exploring the neighborhood of S, all the vertices that have an edge connected to S, and I'm going to keep track of the best way to get there. And as I move away from S and I explore more my graph, I hope to discover more and more paths that will take me there in an optimal way. And when I finish exploring the entire graph, well, I will hopefully have all the right distances. And we will talk about why this works, what is the implementation, and what is the running time of this algorithm. How we can start this greedy approach? Well, we're going to set some key values for the vertices of the graph. We're going to set the distance from S to every other vertex to be infinity at first. And that is on the spirit that you haven't explored the graph yet, so you don't know how you can reach other vertices. So you say, well, I am far away from everybody except, of course, myself. And that's why we set the distance to S to be 0. And now we're going to start moving and exploring the graph. And as we move along edges, we keep track of that path, how it takes us to the final vertex, and we update these key values, distances. So let me show you the implementation that appears on the book. If you did your reading before watching this video, you have seen this slide. I took it literally, like exactly from the book, so it's familiar to you. Here is the part we were talking before. We will start by setting a key value distance to every other vertex in the graph to be infinity, and the distance to S we're going to set to be 0. Now there is also this pre-value of U, which at first we're going to call empty or null or anything you have in mind, really. But this will be a vertex. This will store a vertex, and in my mind, this to me is the parent of every vertex U in the graph, and the parent is the vertex that comes right before U in the optimal path from S to U. Okay, and as we move and update the distances, we are also going to update the parent, and in this way we can recover the optimal path at the end with this array pre of U. Now, how we gonna effectively implement this? We wanna create the vertices of the graph using the distances as key values, and we will approach in a greedy way. We want to take a vertex from H that we will obtain by this procedure delete min that we will discuss briefly soon. And then once we have this vertex U, I'm going to explore all the edges out of this vertex U to another vertex V in my graph. Once I have this, once I am looking at one of these edges, I am going to see if the distance to V, the current value of the distance to V, is bigger than the distance to U plus the weight of the distance or the weight of the edge from U to V. What is this inequality doing? Well, you're saying the distance up to U so far plus the weight of the edge UV is giving me a value that is less than the current distance to V. That means that it's better, if I want to find the shortest path to V from S, it's better to go to vertex U and then to follow the edge UV than doing whatever I stored so far to get to vertex V. And since this is better, since this is shorter, I'm going to update the optimal distance. I'm going to set distance to V to be equal to distance to U plus the weight of HUV. Now, if that is the case, if I am doing this update, I am also going to label the parent of V to VU. What does this mean? This means that the optimal path gets to vertex U and then follows to vertex V. And then, this is like a parent if you follow this optimal path. Finally, we decrease key. This is another procedure that we will explore soon, which takes care of this quick data structure that we're using to implement Dijkstra's. So let's, now that we have this implementation, let's jump into the key procedures and let's discuss the running time. These are the operations we need to implement Dijkstra's. We have this make quick operation, which is basically building a priority quit out of the vertices using the distances, this dist key as keys to build the quit. We have an insert operation, which basically adds a new element to the set. We have a delete min that will return the element of a smaller key value in a given set. And we have this guy will remove this element from the set. And we also have this decrease key, which accommodates the decrease in key value of an element once you change. Remember that we're using the distances as the key values, and we are updating these distances as we implement the algorithm. So it is important to accommodate these key values as we implement the algorithm. So let's talk about the running time of these operations, how long it takes us to do these operations. Making the quit is a one-time operation, and there is no real magic here. We don't do nothing special, or we don't do anything special. And this will take order n, which is the number of vertices, so there is not much to say there. Now, these other operations, insert, delete min, and decrease key, we can think of doing this in different ways. And we will aim, of course, to do it as fast as possible. We can approach this in a naive way. If, for example, I need to return the element of smaller key, I can simply find the smaller key in the given set. And that can take, if I do it naively, that can take length order n, or time, sorry, order n, because n is the worst case scenario of my set, the number of vertices. But if I have to do this every time we explore an edge, we are talking about a running time of order n times m, number of vertices times number of edges for the algorithm. But there's a way to do this better. And to do this, we just need to keep our set of vertices ordered in a more useful way. And this will help us to compute the running time of these operations and to improve in this naive linear time of running time. Now, one way to do this is what is known as binary heap. This is a classical data structure. And what is binary heap doing? Well, it's keeping track of my vertices in a fashion of a complete binary tree. What is a complete binary tree? It's simply a tree in which every vertex has two childs. And the way we store the vertices in this complete binary tree is by filling the tree from left to right, one level at a time, until that level is full. Once we complete the level, we move to the next level and we insert the vertices in each position. Now, how we do this? Well, we want to keep the key values in certain order. And the order is the key value of the parent have to be less or equal than the key values of both its children. In that way, the root has always the smallest key value. And at this point, may be useful to identify each of the vertices with the key value associated to it. So let me give you an example of one of the previous operations in this, or visualize it through this binary heap data structure. For example, look at the tree in part A. This is a binary tree. It's not complete. You have a certain number of vertices, but every vertex has at most two childs. Notice also that the keys are in order such that the parent has a key value less or equal than both its children for every single vertex. And now let's illustrate how inserting a new vertex in this tree will look like. Well, that means, for example, let's say that we want to insert a vertex with key value 7. Since I told you that we will fill this tree from left to right, looking at the current level that is not yet full, that 7 must lie here. That corresponds to the picture labeled as P. Now I need to reorder the key values to fulfill the property that the parent has a key value less than or equal to both the children's. you see that 12 is bigger than 7 and 7 is a child of 12. So we need to improve in that situation. We need to fix that situation. And the way to do that is we let that 7 climb up on the tree until it finds the right position. First, 7 and 12 will swap positions, and now 7 is in good order with 12 and also with 13. But then you look at the pattern of 7 and then you see that 10 is bigger than 7, although 7 is a child of 10. You don't want that, so you allow 7 and 10 to also swap positions. And now you get a new tree in which 7 is the pattern of both 10s and 11, so it is in the correct order. And now you can simply check that the pattern of 7 is also less than 7, it's 3 in this case. So this tree is in the right setting. It's a binary tree, and every vertex key value is less than or equal than both the key values of their childs. Now we're ready to see why or how this data structure could be useful, or one way in which it's useful. To illustrate that with insert, let's see how long it takes us to insert a new vertex in this binary heap. Well, what we have to do when we insert, we place the vertex in the corresponding position, and then, worst case scenario, we allow this vertex to climb up all the way up to the root. So essentially going from the lowest level up to the top. But how many levels can my tree have? Well, we have a vertex at the very top in the root, and then we have 2 vertices in the next level, and then we have 4, and then we have 8. So we have a power of 2 to the k to be precise, at level k. That means that my tree cannot have more than log n many levels, because the total number of vertices is precisely n. Which means that the worst is to allow my new vertex to climb all the way from the log n level to the root, to the first level. Which means that I have to do log n many operations, order O, big O log n if you want, many operations, because every time we simply have to do a comparison. And we will assume that these operations are order 1. So this give me a data structure, this binary data structure allows me to do insert in log n time, which is better than linear time for sure. Let's talk about delete min, getting the mint value in the binary hit. Well, we know what the mint vertex is here. What is the vertex with the minimal key? It's the one at the root. So getting that vertex is very simple. You simply take the vertex at the root and you're done. The problem is that once you remove that vertex from the data structure, you want to keep your order, your tree in the right setting. You want to keep your binary heap correctly, which means I need to move somebody to the root. And of course, a good candidate is a vertex with minimal key. But I don't want to explore which of my current vertices has minimal key, because that might take me linear time. I don't want to do that. And also I don't want, there is a tempting idea, which is, well, I know that the next minimal values will be one of the 2 childs, 5 and 7, because I order my vertices in a way that each level has values less than the next level. But this also runs into trouble, because if you move, for example, 5 to the top, then you need to move somebody 6 or 8 to the position of 5, and then you need to look down and do the same, and this again has the potential to be linear time, worst case scenario. So a simpler way to do this in log n time is I'm going to look at the far most right vertex in the lowest level. In this case, this vertex level is 12, and I'm going to move that to the root. Now that I have a 12 at the very top, I know that this has the potential to be bigger than the childs, and I don't want that to happen. So I let 12, the vertex label with 12 in this picture, to climb down the tree. Just the same operation we did before, but kind of in the inverse order. So I'm going to compare 12 to both my childs, and I'm going to flip the positions of 12 and the lowest child. In this case, 5 is less than 7, and of course less than 12. So I'm going to swap positions with 5 and 12. I'm going to let then these 2 vertices to swap positions, and now 12 is right here. And I repeat, I compare to both childs, and I swap positions with the childs of minimal key value. How long will it take me to do this? Well, I have to go, worst case scenario, from the very top, from the root, up down to the lowest level, and that is again log n many steps, because that is how tall my tree could be. Now we are ready to conclude that the running time of Dijkstra is of order size of the graph, number of vertices plus number of edges, times log number of vertices. How you can see this from the pseudocode we wrote before? Well, we need to create our quit. This is going to be linear in time. We have key values equal to 0 for s and infinity for all other vertices. So there is really nothing to do here. And then we have to do these operations. Every time we loop through the set h, we do this delete min, which we just saw that takes times log of the number of vertices. And we have to do this n times, or v times, because you have to do this for every vertex in the quit. Once you are fixing a particular vertex u, you will look at all the edges out of u, which means that you will look at the edges exactly once. And you may update certain key value if this inequality holds true. And if so, you do this update of the pre or the parent of vertex v. And then you do this decrease key operation or procedure. What does this do? Well, this is just in the case that you update the key value for v, you will need to move the vertex v in your binary heap, because now your key changed and there is a potential of a son or a child being less than the parent. But we saw that this operation is also log v. Now you do this for every edge, and you do this for every edge exactly once, which means that the worst case performance will be size of the number of edges, size of e, times log v. And that adds up to the running time that we're showing here in red.